So today we're going to start with redox chemistry. Okay, so we're going to look at redox reactions and redox processes. But before we do that, we're gonna first try to understand what is a redox reaction and where we get the name reduction and oxidation from. Okay, so redox reactions. Okay, in the simplest sense, okay, redox reactions are reactions that involve electron exchange. Okay, that involve electron exchange. Okay, so there's some gain of electrons, some loss of electrons. Okay, some things gain electrons, some things lose electrons. Okay, so the reactions that involve electron exchange. So when we talk about redox processes or redox reactions, okay, we're talking about gain of electrons and loss of electrons taking place. Okay, so gain and loss of electrons are taking place. So you can say that the reactions that involve electron exchange, or you can also say that the reactions that involve changes in oxidation number. Okay, we'll talk about oxidation numbers in just a bit. But let's first see where this idea of what we mean by a redox reaction, where it comes from historically. So for example, let's look at the reaction between aluminum oxide and carbon. Okay, Al2O3 reacts with carbon to form aluminum and carbon dioxide. And if you balance this equation, okay, you have 2Al2O3, you have 4Al here, you have 3CO2 and 3C. If you look at this reaction, one observation you can make is that the mass of the solid decreases, right? This is, you're extracting aluminum metal from the aluminum ore, right, the rock, the mineral. And what we see is that this aluminum oxide, this is your initial starting solid, right? And when it loses oxygen atoms, right, the mass of the solid decreases. So the mass of the ore or the aluminum oxide is greater than the mass of the aluminum obtained, right? So historically, this is where the name reduction came from. Okay, because when we extracted metals from their ores, the loss in mass was due to a loss of oxygen, right? And that loss in mass was referred to as reduction in mass. So historically, the loss in oxygen was referred to as reduction. So over here, we can say that aluminum oxide is being reduced. Okay, aluminum oxide is being reduced because it is losing oxygen. Okay, so loss of oxygen is referred to as reduction. Okay, again, historically, when metals were extracted from their ores, because a reduction in mass was observed, and we knew that that reduction in mass was due to the loss of oxygen, we said that reduction refers to the loss of oxygen. Okay, this is not the best way of defining reduction anymore, but this is where the name reduction came from. And the reverse, which is the gain of oxygen, was referred to as oxidation. Okay, so over here we can say that carbon is being oxidized. Right, carbon is gaining oxygen, so we can say gain of oxygen. Right, so aluminum oxide loses oxygen, reduction in mass, hence the name, that's where the name reduction came from. And then over here carbon is gaining oxygen, right, so we say that carbon is being oxidized. Now let's look at the next reaction. Let's look at the combustion of methane. Right, we have CH4 reacting with oxygen to form carbon dioxide and H2O. And here we have 2O2 and then 2H2O. So over here we can say that methane is being oxidized because it's gaining oxygen, right? So methane is being oxidized. So we can say that methane is oxidized, right? Because here we can see that carbon is gaining oxygen. And another way of looking at redox reactions is that it's losing hydrogen. Okay, whenever you're losing hydrogen, that is also referred to as oxidation. So since there's a loss of hydrogen here, right, methane is losing hydrogen, we can say that it's undergoing oxidation. Now over here we can say that oxygen is undergoing reduction, okay, because it is gaining hydrogen. Okay, gain of hydrogen. Now again, these are not the best ways of looking at redox reactions, right? This is how historically we've looked at redox reactions. We said historically we said that, you know what, if there's a loss in oxygen, we call it reduction. If there's a gain in oxygen, we call it oxidation. Then we said that, okay, if there's a loss of hydrogen, we're going to call it oxidation, and there's a gain of hydrogen, we're going to call it reduction. Okay, but there are going to be redox reactions that don't involve oxygen and hydrogen at all. Okay, but this will always be true. Reactions that involve electron exchange, gain and loss of electrons, okay, or reactions that involve changes in oxidation number will be referred to as redox reactions. Okay, so any reactions that involve electron exchange or changes in oxidation number, okay, changes in oxidation number are referred to as redox reactions. So this is what we're going to be looking at in detail when we study redox reactions. Okay, we're going to be looking at electron exchange, and we're going to be looking at changes in oxidation number. Another thing to observe is that reduction and oxidation always occur simultaneously. Okay, reduction and oxidation always take place simultaneously. So if you look at the first reaction, for example, right, in order for aluminum oxide to undergo reduction, right, in order for it to lose oxygen atoms, something else has to accept those oxygen atoms, right? So in order for this guy to undergo reduction, carbon has to undergo oxidation, because this guy can't undergo reduction until and unless something else will accept the oxygen. So that means that if aluminum oxide will undergo reduction, something else must be undergoing oxidation, right? Some atoms must be undergoing reduction and some atoms must be undergoing oxidation. Similarly here, this reaction will often be referred to as the oxidation of methane. That doesn't mean that only oxidation is taking place. Reduction is also taking place. When we're talking about methane, it's oxidation of methane, right? So when methane is the subject, we say combustion reactions or oxidation reactions, right? Because when we talk about combustion reactions, our subject of conversation is methane. We're talking about the fuel being combusted. So the fuel itself is being oxidized, but oxygen is being reduced, right? So in order for something to undergo oxidation, something else has to undergo reduction, or vice versa. Okay, so this oxidation of methane is also a redox reaction. We just refer to as oxidation sometimes because we're specifically talking about methane, but it's a redox reaction. So reduction and oxidation will always occur simultaneously. If there's oxidation taking place, there must be reduction taking place, and vice versa. Now, if you go back to the first reaction, my question is, which of these species is the oxidizing agent? Now, aluminum oxide is the oxidizing agent, right? The species that undergoes reduction is the oxidizing agent, okay? The species that undergoes oxidation is called the oxidizing agent, okay? So this is the oxidizing agent, right? It's undergoing reduction, and because it's undergoing reduction, it's causing something else to be oxidized, okay? So this is called the oxidizing agent. And then the species that undergoes oxidation is called the reducing agent, right? It's accepting the oxygens here, it itself undergoes oxidation, it's causing something else to be reduced, okay? So we can say that carbon here is the reducing agent, okay? Similarly, here methane was undergoing oxidation, so methane is the reducing agent, okay? Methane is the reducing agent, okay? And oxygen is undergoing reduction, okay? Oxygen is the oxidizing agent. So we can say that the reducing agent undergoes oxidation, okay? The reducing agent undergoes oxidation and the oxidizing agent undergoes reduction, okay? Reducing agent undergoes oxidation, and then the oxidizing agent undergoes reduction. So here's a table of what we mean by oxidation and reduction, okay? Oxidation, reduction. Oxidation refers to a gain of oxygen. Reduction refers to as a loss of oxygen. Oxidation may also refer to as a loss of hydrogen. Reduction can be referred to as a gain of hydrogen. As I said, these are older ways and less precise ways of defining oxidation and reduction. The more precise ways of defining oxidation and reduction are the following, right? Oxidation is referred to as a loss of electrons. Okay, so whenever we have a loss of electrons, that is referred to as oxidation. Okay, and when you have gain of electrons, it is referred to as reduction. Okay, so gain of electrons is reduction. Similarly, an increase in oxidation number, an increase in oxidation number is referred to as oxidation. Okay, and a decrease in oxidation number is referred to as reduction. Decrease in oxidation number is referred to as reduction. Okay, so these are more precise ways. Okay, these are more precise ways of defining oxidation and reduction. Okay, that oxidation can be referred to as the loss of electrons or an increase in oxidation number, and reduction can be referred to as the gain of electrons or a decrease in oxidation number. And this is what we're going to be studying in detail in this chapter. Okay, we're still going to be looking at this definition as well, gain of oxygen or loss of oxygen or loss of hydrogen, gain of hydrogen. Okay, but they're not the most precise ways of defining oxidation and reduction. Okay, this is really the crux of redox reactions, right? When we have exchange in electrons or when we have changes in oxidation number. So we're going to look at oxidation numbers and the rules for assigning oxidation numbers to different atoms and different compounds and ions. Okay, so what we have is I'm going to talk about oxidation numbers, right? Firstly, of course, we know that an increase in oxidation number is referred to as oxidation, right? So oxidation is when we have an increase in oxidation number, right? And then reduction is when we have a decrease in oxidation number. Now let's look at the rules for assigning oxidation numbers. The first rule that we have is that atoms in elements, okay, always have an oxidation number of 0. Okay, always have an oxidation number of 0. So for example, if we were talking about sodium metal, what's the oxidation number of sodium? It's an element in a standard form, right? It's 0. If we were talking about fluorine gas, right, what's the oxidation number of the fluorine atom, of both fluorine atoms is 0, right? We're talking about sulfur solid, S8, what's the oxidation number of each sulfur atom? 0. Okay, so in any element in standard state, okay, for any elemental substance, the oxidation number will always be 0. So whenever we're talking about non-zero oxidation numbers, we're only going to be looking at ions and compounds. Okay, elements mein it'll always be 0. Okay, so now let's look at the rules for compounds and ions. Okay, for compounds and ions, we may have non-zero oxidation numbers as well. We can have 0 still. We can also have non-zero oxidation numbers. Okay, so for compounds and ions, group 1 elements will always have an oxidation number of +1. Group 2 elements will always have an oxidation number of +2. Group 13 elements in compounds and ions will always have an oxidation number of +3. Right, remember aluminum is in group 13, okay? not group 3, group 13. Fluorine will always have an oxidation number of -1. Okay. Fluorine is always -1. Not all the group 17 elements will always be -1, okay, but fluorine will always be -1. Then oxygen is -2, okay, except when it's bonded to fluorine, except when it's bonded to fluorine, or in peroxides. Hydrogen, okay, has an oxidation number of +1 when bonded to nonmetals, okay, when bonded to nonmetals, okay, and the oxidation number is -1 when bonded to metals. All right, the next rule that we have is that the overall oxidation number, okay, the overall oxidation number for a neutral substance or compound is 0, and the overall oxidation number for an ion, okay, the overall oxidation number for an ion is the charge on the ion. Okay. Number for an ion is the charge on the ion. Now let's briefly look at where we get these rules from, or some of these rules. Okay, like for example, why is fluorine always -1 but oxygen isn't always -2? Like why is it not -2 sometimes? So for example, right, let's say that we have hydrogen fluoride. What's the oxidation number of fluorine? The oxidation number of fluorine is -1. So then what's the oxidation number of hydrogen? So the oxidation number of hydrogen is +1. Right? Because again, the overall oxidation number for this compound, it's a neutral compound, is 0. So it's +1 -1, so that will be 0. Now let's look at the next example. Let's look at the example of H2O. What is the oxidation number of oxygen? The oxygen has an oxidation number of -2, right? And each of the hydrogen atoms are +1. Now if you look at F2O, let's say, F2O or OF2, that's basically oxygen bonded to 2 fluorines. Now what's the oxidation number on fluorine? -1, right? Because fluorine will always be -1. So then what's the oxidation number on oxygen? +2, because the overall oxidation number is 0. So if this is -1 -1, that's -2, then oxygen has to be +2. Now why is this the case? Why is fluorine always -1? Okay, when we're assigning oxidation numbers in covalent compounds, right? Again, oxidation numbers can apply to ionic or covalent substances. For ions, it's just a charge, right? But for covalent substances, we're looking at electronegativity. When we look at HF, fluorine is more electronegative than hydrogen, so fluorine will get the negative oxidation number and hydrogen will get the positive oxidation number. Now if you look at H2O, right, again, oxygen is more electronegative than hydrogen, so oxygen will get the negative oxidation number and hydrogen will get the positive. Right, you have 2 single bonds, so each of the hydrogens is +1, which means that the oxygen is -2. Now between oxygen and fluorine, fluorine is the more electronegative element. Because fluorine is the most electronegative element, it will always be -1, because it always either makes F- ions, fluoride ions, or it makes single bonds. So fluorine will always be -1. So when it's bonded to oxygen, because oxygen is less electronegative, fluorine will get the negative oxidation number, and therefore in this compound, oxygen has an oxidation number of +2. Because oxygen is almost always -2. But then when it's bonded to fluorine, right, oxygen is more electronegative than everything except fluorine, right? It's the second most electronegative element. So when it's bonded to fluorine, then fluorine will get the negative oxidation number. So electronegativity can be used to explain these rules for covalent and ionic substances. Okay, but it's especially helpful when we're talking about covalent substances. So another example I want to look at is that of hydrogen peroxide. Okay, hydrogen peroxide is H2O2. Okay, and it has the following structure. Okay, we have a hydrogen bonded to an oxygen, bonded to another oxygen, bonded to a hydrogen. Okay, now over here what we have is the hydrogens have an oxidation number of +1. So each of the oxygens have an oxidation number of -1. Okay, the peroxide ion is just O2 2 minus. Okay, this is called the peroxide ion. Okay, the peroxide ion. In this, we have each oxygen has an oxidation number of -1. Okay, so the overall oxidation number for the ion is obviously -2, right? That's just the charge on the ion. So this is hydrogen peroxide or the peroxide ion. In this, the oxygen has an oxidation number of -1. So those are the two exceptions where oxygen is not -2, right? Either when oxygen is bonded to fluorine or when it's bonded in peroxides.